Ants are everywhere. These tiny insects are some of the most ubiquitous creatures on Earth, found in nearly every corner of the globe. From the dense rainforests to the arid deserts, ants have adapted to thrive in a variety of environments. We see them on sidewalks, in our gardens, and even in the cracks of city pavements. Their presence is so common that we often overlook the incredible complexity of their lives. Sometimes, they even make their way into our kitchens, scavenging for crumbs and tiny morsels of food. But what we see on the surface is just a glimpse of their fascinating world. These tiny creatures may seem insignificant, but they live in complex societies. Each ant has a role to play, from workers and soldiers to the queen who ensures the colony's survival. Ant colonies are like bustling cities with millions of individuals working together in harmony. They build intricate nests, forage for food, and defend their territory with remarkable efficiency. For thousands of years, scientists have been fascinated by ants. Their social structures and behaviors offer a window into the principles of collective behavior and cooperation. How do they build these intricate nests? Using nothing but their tiny bodies and a collective effort, ants can construct elaborate underground cities that rival human engineering. How do they communicate and cooperate so effectively? Ants use a combination of chemical signals, touch, and even sound to relay information and coordinate their activities. To understand these questions, researchers have turned to computer simulations. These advanced models help scientists decode the complex algorithms that govern ant behavior. These simulations act as virtual laboratories, allowing us to observe ant behavior and test theories about their social organization. By manipulating variables, researchers can see how ants respond to different challenges and environments. By studying these simulations, we gain insights into not only the lives of ants, but also the principles of collective behavior, adaptation, and resilience. These tiny creatures teach us about the power of cooperation and the intricate balance of ecosystems. An ant colony simulation is a computer program. It recreates the life cycle and behaviors of an ant colony. Think of it as a digital ant farm, but much more sophisticated. These simulations use mathematical models to represent individual ants and their interactions. Each ant in the simulation follows a set of simple rules. These rules dictate how it moves, searches for food, communicates with other ants, and responds to its environment. By observing how these simple rules lead to complex colony-level behaviors, we can gain a deeper understanding of how ant societies function. Imagine a day in the life of an ant colony. The colony wakes up as worker ants emerge from their nest. They are driven by a collective purpose to find food, care for the brood, and defend the colony. Worker ants have specific roles. Some ants are foragers, leaving the nest to search for food. Others are nurses, caring for the eggs and larvae. Still, others act as soldiers, protecting the colony from invaders. Throughout the day, ants communicate with each other using pheromones, chemical signals that convey information. For example, foragers lay down pheromone trails to guide other ants to food sources. Ants are incredibly efficient foragers. They have evolved over millions of years to perfect their methods of finding and collecting food. This efficiency is not just a result of individual effort but a highly coordinated system that involves the entire colony. They use a decentralized system to find and retrieve food. Each ant operates independently, yet their collective behavior results in a highly organized and effective foraging strategy. This decentralized approach allows them to cover large areas and quickly locate food sources. When a forager finds food, it lays down a pheromone trail back to the nest. This chemical trail serves as a guide for other ants, leading them directly to the food source. The use of pheromones is a brilliant adaptation that ensures the colony can efficiently exploit food resources. Other ants follow this trail, reinforcing it with their own pheromones. As more ants travel the path, the trail becomes stronger and more defined, making it easier for additional ants to find and follow. This positive feedback loop ensures that food is quickly and efficiently transported back to the nest. If a food source is abundant, the pheromone trail becomes stronger, attracting more ants. This ensures that the colony can take full advantage of plentiful resources. The more food there is, the more ants are recruited to collect it, maximizing the colony's efficiency. If a food source is depleted, the pheromone trail weakens, and ants stop following it. This dynamic system allows ants to adapt quickly to changing conditions, ensuring they do not waste time and energy on exhausted resources. Ants also have sophisticated defense mechanisms. Their ability to protect the colony is just as important as their foraging skills. defense roles are crucial for the survival of the colony, especially in environments where threats are constant. Soldier ants are larger and stronger than worker ants. These specialized ants are equipped with physical adaptations that make them formidable defenders. Their size and strength allow them to fend off predators and protect the more vulnerable members of the colony. They protect the colony from predators. Whether it's a larger insect or a small mammal, soldier ants are always ready to defend their home. Their aggressive behavior and physical prowess make them effective at repelling intruders. Some ant species even have specialized soldiers with powerful jaws for crushing enemies or bodies filled with toxic chemicals. These adaptations provide an additional layer of defense, making the colony even more resilient against threats. The diversity of roles within an ant colony is a testament to their evolutionary success. The study of ant colonies has inspired a field of computer science called ant colony optimization. This field uses algorithms based on ant behavior to solve complex problems. For example, ant colony algorithms can be used to find the shortest route between 2 points, optimize traffic flow in cities, or even design more efficient communication networks. These algorithms work by mimicking the way ants use pheromone trails to find the shortest path to a food source. By applying these principles to other problems, we can develop more efficient and robust solutions. Section 6 Fun Facts: The Marvels of Ant Colonies. The world of ants is full of fascinating facts. Did you know that there are over 12,000 known species of ants worldwide? The total weight of all ants on Earth is estimated to be equal to the weight of all humans. Some ant species can lift objects up to 50 times their weight. Ants communicate using a variety of signals, including pheromones, touch, and sound. Some ant species engage in ant wars, where colonies battle each other for territory and resources. Section 7. Learning from ants, ecosystems, and technology. Studying ants is not just about understanding these fascinating creatures, it also has important implications for our understanding of ecosystems and the development of new technologies. Ants play a vital role in many ecosystems. They help to disperse seeds, improve soil aeration, and control pest populations. By studying ant colonies, we can learn more about the delicate balance of nature. Furthermore, the principles of ant behavior can inspire the design of more efficient and resilient systems. From robotics to artificial intelligence, the study of ant colonies has the potential to drive innovation in various fields. Section 8. Conclusion: The future of ant simulation. As technology advances, ant colony simulations are becoming increasingly sophisticated. These simulations are not just simple models, they are intricate systems that mimic the complex behaviors and interactions of real ant colonies. By observing these virtual ants, researchers can gain insights into how ants communicate, cooperate, and solve problems. With the help of artificial intelligence and machine learning, we can create simulations that are more realistic and predictive than ever before. These technologies allow us to analyze vast amounts of data and identify patterns that would be impossible to detect manually. For instance, AI can help us understand how ants optimize their foraging routes or how they adapt to changes in their environment. These simulations will allow us to explore new questions about ant behavior, ecology, and evolution. We can study how ant colonies respond to different environmental pressures, how they evolve over time, and how they maintain their complex social structures. This knowledge can be applied to a wide range of fields, from ecology and biology to robotics and artificial intelligence. They will also provide valuable insights for developing new technologies and solving complex problems in various fields. For example, the algorithms used by ants to find the shortest path to food sources can inspire new approaches to network optimization and logistics. Similarly, the way ants work together to build their nests can inform the design of autonomous robots that need to collaborate on construction projects. The study of ant colonies, both real and virtual, is a testament to the power of collective intelligence and the remarkable adaptations found in the natural world. Ants have evolved sophisticated strategies for communication, cooperation, and problem-solving, and by studying them, we can learn valuable lessons about resilience, efficiency, and innovation. By continuing to explore the world beneath our feet, we can unlock new discoveries and innovations for generations to come. The future of ant simulation holds great promise, not only for understanding these fascinating creatures, but also for applying their lessons to human challenges. As we delve deeper into the intricacies of ant behavior, we open the door to a wealth of knowledge that can benefit science, technology, and society as a whole. Section 9. Acknowledgments. This essay was made possible by the generous support of the National Science Foundation and the Stanford University Department of Biology. I would like to thank my colleagues and collaborators for their invaluable contributions to our research on ant colonies. A special thanks to all the students who have participated in our research and outreach programs, inspiring the next generation of scientists and engineers.